Okay, hi everyone. My name is Jakob van den Eijnden. Indeed, I'm a junior research fellow at the University of Oxford, and I'm calling in from Oxford now as well. And indeed, I want to talk about the inflow-outflow coupling of strongly magnetized accreting neutron stars for the next 15 minutes or so. The main takeaway message of this presentation, if there's one sort of key message for you to take out of it, is that with our recent work, we can now say that transient accreting neutron stars, regardless of whether they are weakly or very strongly magnetized, show evidence for a global X-ray radio correlation. This is argued in all detail in a paper that came out last August. You can see the archive link there. This paper also includes a GitHub reproduction repository, which means that if you want to play with any of the data, or if you want to use any of our data for your own work, you're free to go there and grab it and run with it. So, as the title of my talk suggests, I want to talk about X-ray and radio emission from binary systems, and we've heard about this a lot, of course, already, about radio emission from these systems. So why we care about these specifically is, of course, that they're probing the jet, typically, in X-ray binary systems, which give us a probe of the feedback power, the energy budget for feedback from X-ray binaries. They are a regulatory presence for angular momentum and possibly a probe for compact object spin in these systems, but also on much larger scales within the universe and a much wider range of systems that launch jets. X-ray binaries can be very interesting to study jet launching models, both in black hole systems and in neutron star systems. However, a lot of the knowledge that we have about jets from X-ray binary systems historically has been based on low-mass X-ray binary systems and transient low-mass X-ray binary systems. So here on this slide, you see on the left an image that we already saw in the previous talk in a different version as well, where you see the typical outburst evolution of a black hole, a transient black hole low-mass X-ray binary, where it's highlighted how the jet and the jet properties change throughout the outburst, going from something that we call a compact steady jet in the hard state to more discrete ejecta as the source transitions, and then a quenched jet in the soft state. Now, if we zoom into that hard state and that hard state compact jet, on the right, what you can establish observationally is that there's a coupling between the X-ray and the radio luminosity. So the X-ray luminosity is shown there horizontally, probing the accretion rate. The radio luminosity is showing vertically, probing the jet power. And the black points for black holes show you that over a wide range of accretion rates, there's a correlation. So physical coupling between the X-ray, so the accretion rates, and the radio, the jet power. In the reddish points, you also see neutron star, transient neutron star, low-mass X-ray binaries plotted, which as a sample show a similar correlation, but there's a couple of caveats to make there. First of all, these systems are radio fainter, as you can see. As a result, they've only been radio detected over a more narrow range in accretion rates. And also, you may argue that there's a bit more scatter in the neutron star systems. However, I want to highlight again that these are low-mass X-ray binaries that these studies have been done with, and that's important for the neutron star systems because the neutron stars in low-mass X-ray binaries are almost always weakly magnetized and fast spinning. So with weakly magnetized in this context, I mean about 10 to the 8 Gauss order of magnitude. However, that leaves out the entire population of high-mass X-ray binaries in this context. And high-mass X-ray binaries are quite different in this sense. They're about half of the X-ray binaries in our galaxy. But if you look at the neutron stars in high-mass X-ray binaries, those are much more strongly magnetized, typically 10 to the 12 Gauss or more. And neutron stars also make up the vast majority of accretors in high-mass X-ray binaries. However, studying jets in these systems is quite challenging. I've summarized that here in sort of 4 keywords. Where the fewer refers to the fact that if you look before, say, about 5 years ago, there's only 3 systems which are likely black hole systems that had been studied in radio and had been studied in terms of their jet properties. It's quite hard actually to do jet studies in high-mass X-ray binaries for a very simple reason, which is that there is a massive star sitting there as well, which can complicate things. First of all, because the massive star has a strong stellar wind that can have its own radio emission that may dilute any jet emission. But the massive star can also absorb through its wind part of the radio emission from a jet. I've written down here that they can also be better in certain senses to study jets, and that's specifically for those neutron star high-mass X-ray binaries. Because if we study jets in those systems, we're opening a very new, poorly explored parameter space for jet models. Specifically, again, that where the neutron star is very strongly magnetized and slowly spinning. Now, that's relevant specifically for neutron star jet models, where we have a subset of models that predict that these systems shouldn't launch jets at all, and a set of more recent simulation-based models that predict that even those systems can launch jets. However, the final challenge is that these systems are fainter. For many decades, people have observed neutron star Hymas X-ray binaries in radio without detecting any emission. And that shows us that even if we can try to study them, they will have to be faint in radio, which makes it a challenge. So before the paper that I want to talk about today, the sort of picture was really based on two sources that we had. And these are two neutron star Hymas X-ray binaries. On the left, you see BP Crew, which is a radio detection here in the square in the image. This is a persistently accreting Hymas X-ray binary, and in that source, it's still somewhat unclear what is causing this radio emission, whether it's the stellar wind or maybe a transient jet contribution. A more clear case for a jet was seen in the source on the right, Swift J0243, which is a transient neutron star Hymas X-ray binary. It was discovered in 2017 in a massive super-Eddington outburst, and as you can see here in the light curve, it wasn't only detected in X-rays in gray, but we also were able to detect it and follow it and track it in the radio throughout the outburst. Now, one striking thing of our radio monitoring is that it showed that the radio and the X-rays peaked around a similar time and showed a similar coupled decay in luminosity, which is very reminiscent of low-mass X-ray binary systems. And through that observation and several other observed properties, we concluded that the most likely origin of the emission is a jet. However, based on that sort of information, you can already formulate a sort of list of open questions. So I've listed here a biased list of those. And the first of that is whether if you see any sort of coupled behavior in X-ray and radio in these systems, whether this is just a super-Eddington thing, simply because we had only seen it at that point in a super-Eddington outburst. And if it's not, whether basically all transient neutron star Hymas X-ray binaries will show this. If so, if they are all as radio faint as these sources that I just showed on this last slide, and if there's any difference between these transient and persistent sources. Now, for this talk, I'll focus mostly on the transient systems, because if we want to talk about an X-ray and radio coupling, it's easier to do that in a transient system, which ranges through a large range of accretion rates. And also, these systems tend to have somewhat weaker stellar winds, which eases the challenge that those stellar winds bring. Now, this is again the key statement that I'd like you to take away from this presentation, which is that transient accreting neutron stars in both the low and high magnetic field case show evidence for this coupling. So what do I base this on? Because so far I've just shown this very briefly for one source. Well, I base this on new campaigns that we've done since then, which can be summarized as 2 telescopes, 3 targets, and 4 outbursts. The two telescopes, are the VLA and EDCA for different hemispheres. The 3 targets are listed here on the slide, which are all 3 Hymas X-ray binaries with a slowly spinning, strongly magnetized neutron star in them. And the 4 outbursts are 4 different outbursts that these sources had in the past couple of years. Now, due to time constraints, I'm not going to discuss the first 2 sources. We did not detect any radio emission in them due to distance and sensitivity constraints. But I'm going to go into a bit of depth about the third source, 1A0535, because this is the one we did detect in radio. So you may have heard of 10535. It's a well-known neutron star Hymas X-ray binary. It's been known for many decades, and it's, as you can see here in this light curve, very clearly a transient source. This is a light curve of about 18 years of X-ray monitoring, and you can see these very bright but brief outbursts in activity. In late 2020, early 2021, it showed, as far as I know, the brightest ever recorded outburst reaching more than 11 crabs. And this is the one that we also targeted with the VLA. Now, what you see here, I already gave a bit of a spoiler, is that we do indeed detect radio emission with the VLA for this source. This is a faint but significant radio detection. But if you look at the color scale on the top here, it only goes to about 50 microjansky. So for those of you familiar with radio units and radio telescopes, that is really, really faint for jets. That's not the only radio detection we obtained. So this is the full X-ray and radio light curve of the main outburst. What you see here is about 5 months of activity, where there's a single month at the start, which has the main activity that reached I'd say about 10% Eddington or so, a bit more maybe. In gray, black, and red, you see the X-ray behavior, and then in blue, you see the radio outburst. And what you can see is a couple of things. First of all, the radio is not always detected. We only get detections during this main peak of the outburst. And the radio also peaks in a similar way as the X-rays. It peaks at a similar time, and we see a similar decay timescale in the radio. Now, this, again, coupled outburst behavior that we see in X-ray and radio motivated us to also put this source and the other neutron star Hymas X-ray binaries we observed on this X-ray radioluminosity diagram. So there's quite a bit going on in this diagram. I'll walk you through it. In gray, we have the Lomas X-ray binaries that I showed before. So the black holes in the crosses, the neutron star Lomas X-ray binaries in the circles. And then we have these bold points, which are all neutron star Hymas X-ray binaries.
3 minutes.
Oh, sorry?
3 minutes.
Okay, thank you. The open squares are persistent systems, which I'll get back to at the end very briefly. The filled squares are the transient systems, and the detections are really predominantly located in the bottom right. So very bright in X-rays, very faint in radio. Now what we did here is basically treat these the same way people treat Lomas X-ray binaries and say, can we as a population find a correlation between the X-ray and the radio? When we do, and when we combine these different sources, we find the following fit, which if we do a proper statistical analysis has a pretty similar slope to the Lomas X-ray binary systems. However, as you can see here on the slide, it's incredibly faint compared to the other types of systems, more than 6,000 times fainter than the black holes. Now that it can also be shown in a sort of schematic version where I want to highlight here in this sort of schematic version of the same diagram, where the green data or the green region is the transient neutron star Hymas X-ray binaries. The yellow region is where the persistent neutron star Hymas X-ray binaries are located. And then I want to highlight that these persistent sources seem to be somewhat radio bright compared to this correlation, this coupling that we find. So if we get back very briefly to that bias list of open questions, we can already say that this is not just a super-Eddington behavior. We see this now in the second source that's not super-Eddington, but of course you have to wonder what you're actually applying physically when you're fitting together with one super-Eddington and one sub-Eddington source. We also find supportive evidence that these transients are all very radio faint. In fact, when we go below 10% Eddington or so, or 1% Eddington, we really need future generation telescopes to see them in radio. The origin for this radio faintness is still hard to understand. My suspicion is that it's a combination of magnetic field and spin, but it doesn't so far follow the scaling that has been proposed in recent jet models for these systems. Now, finally, there is this difference apparently between persistent and transient systems in their radioluminosity. So what could be the origin for that? And I want to end on that very briefly because this is future work that I'll be working on. A main idea that we're exploring now is that this may have to do with the ambient density in and just around these systems, where if you can think basically about a scale in density from low mass X-ray binaries, where there's very little material, to very extreme systems that are still, for example, embedded in their supernova remnants, and in between there, you'll go through regions where sort of in high mass X-ray binaries, from transients to persistent sources, you'll get a higher wind density surrounding the system or in the system. You can imagine that a jet being launched will immediately interact with that, and that may give an extra mechanism to dissipate energy and to radiate energy away. This is still just a working idea, so we're doing more observations to gather more data to test this, and I'll also be working on more actual modeling and understanding of this to see if it's consistent with the observations that we already have. So I'd like to leave you with my conclusions. I think I'm very close to the 15 minutes. Basically that we are detecting 1A0535 in radio, and I'll also find an X-ray radio coupling. We don't detect the other two sources that we targeted, but overall for this type of source, we now see a radio X-ray luminosity coupling over almost 3 decades in X-ray luminosity. We do, however, see that this is incredibly faint compared to other types of neutron stars and black holes in X-ray binaries, and the exact origin of this is still not completely sure. So let me end with a shameless plug for this archive paper here, which is focusing more on persistent systems, if you're interested in that. And I'll leave you again with this takeaway message, which is that transient neutron stars, regardless of magnetic field, show evidence for a global X-ray radio coupling. Thank you.